The format for today is this is a zk Meetup series and the 20th instance, a very round one. And we will start with a quick talk by Thomas on TLSNotary and zk. Thomas came just for this from a very far distant country of Germany. We are in Poland here. And after the talk, we'll have a quick bite, some pizza, some drinks. Suit yourselves to those. But we will also have the opportunity for questions after, unless you prefer to take questions as you go.
Let's probably do it afterwards. I think then we can more focus on the questions.
Yeah, gotcha. Other than that, a huge thanks to Ethereum's ESP ecosystem support program for supporting zkWarsaw, and also a huge thanks to Gosia from Vilea from running all of the logistics around this and our crew. Thomas, please go.
Thanks. Okay. Yeah, hi everyone. My name is Thomas, and I'm here to tell you something about TLSNotary today. So the title of the talk is TLSNotary, a mental model. And so for those of you who don't know, TLSNotary is an implementation of a zk TLS protocol, which uses MPC for this purpose. So I've structured the talk basically into three parts. So in the first part, we'll have a look, get some overview about what TLSNotary is and what it can do. And then we'll have a look at the cryptography which is involved there. And in the last part, we'll see where this cryptography is used in TLSNotary and how it is used. Okay, but a few words about the project TLSNotary. So TLSNotary is a project inside of PSE, and PSE is short for Privacy and Scaling Explorations, which is a team inside of the Ethereum Foundation. And what's PSE? What they do is basically provide implementations of cryptography for open source use cases, and also a little bit applied research. All right. Okay, so first I should probably tell you about what's the problem that TLSNotary is trying to solve, and the problem is the portability of web data, right? So let's just imagine for a second you're Alice and you're visiting a website. So you're probably using HTTPS for that, and now a server serves you the website, but what you can now not do is forward these data in a credible way, right? So for example, if you have some entity, Bob has he cannot know about the origin or the true origin of the data Alice just forwarded to Bob, right? So, and there are many use cases why you might want to do this. So think of, for example, you have your government has a server and it has some data about you and your identity, and you might want to forward that to some KYC provider. Or like in banking, there are different applications for that. Like you would show your banking information to some creditor and get some loan. Yeah, and even connecting Web 2 and Web 3, there are interesting use cases for that. All right. So this currently doesn't work with TLS.
Why?
Yeah, why? We'll come to that in a second. Okay. So what's, maybe for those of you who don't know what's TLS, I mean, if you have the internet, you have this TCP/IP protocol, which basically ensures that you are connected to another machine, and then it meters the connection and the bandwidth which it uses. And then above that, there's transport layer security, or TLS protocol, which is, so to say, the cryptographic layer, and it makes sure two things. One is authenticity, so that you're really connected to the right entity, and the other one is the confidentiality, that their data in transit is encrypted. And when you connect to a website, you use HTTPS, which is HTTP with TLS on top or below. Yeah. Right. So, and coming back to the beginning, you get this authenticity and confidentiality, but what you don't get is the portability of your data. And there's a term in cryptography for that, which is called non-repudiation. So Bob has no he can't know about where these data are from. So, and to answer this question, what's the reason for why this doesn't work is because TLS ultimately uses symmetric key cryptography for the encryption and decryption. So that means that Alice has the same key like the website or the server. So Alice can just come up with some arbitrary data, encrypt it, and then basically send it to Bob and pretend it was sent by the website or by the server. And now we come to the bright future TLS with TLSNotary. So Alice basically runs a normal TLS connection with the website, and then Alice runs this TLSNotary protocol with Bob. We'll see in a second what that means in detail. But you get authenticity and confidentiality of the TLS data like before, but now you get some nice features on top. So the first thing is the portability of your data, and we'll see that it's not only portability like Alice, so to say, forwarding everything. You also get some sort of degree for the privacy, or basically you can do some assertions about the data in zero knowledge, or you can only selectively disclose parts about that. Yeah. So the nice thing is that in this setup, there's no trust required, because when Bob is the verifier of the data, then just Alice in some sense really proves to Bob facts about the data. So no trust assumption in this setup, only when you run a notary server. And it's invisible to the website, which is also quite nice. Because there are some use cases where the website might censor this use case. On top of that, you need no modifications to the TLS protocol, right? So it's in some sense an add-on. Okay, so before we look into how TLSNotary does it, we have a look at potential other solutions. So the most simple solution would just be to sign the data at the source, so the website. I mean, from DNS, the website basically has a public key, and now it can basically hash the data and then sign it and then send it over to Alice, and then Alice can easily forward it to Bob, and Bob can just check the signature on it against the public key of the website, right? So this is in some sense the right solution or the most elegant solution, but you need the websites to implement it. I mean, you can do it on the application layer. That would be then for HTTP. I think there's even some sort of standard called SXG, I think, for supporting that in some sense of HTTP header. But you can also modify TLS, but that takes some time to be deployed, right? So that's it for signing the data. So what you can also do is you can delegate the access, basically, that when you have a website who wants to know some information about you, the website can send you to so to say to the data provider, and then you can consent that you want to grant access to this website requesting the data. But that comes with its own issues, because now the data provider, it sees what you want to do with your data, because it sees the domain name or where this request is coming from, right? And there's also some privacy issues with that. So the website also needs to implement this OAuth protocol. Also not ideal. And another approach which is quite interesting at the moment is this proxy approach, right? Where that's basically when you put the verifier in between Alice and the website. So when you do a request, you send your request to the proxy forwards it to the website answers with response, and proxy also forwards this to you. And in this setting, you wouldn't need any cooperation from the website. But now you're using basically one IP for everything, so it's easy to block, right? Because it's always from the same IP, from the proxy, right? All right. Okay, and even if in this proxy world, even if the proxy only sees the encrypted traffic, the proxy still knows the website where it's now connected to. So also some privacy issues. And the last thing is there are some network assumptions when you consider the security of the protocol, because think of you have an almighty prover, like Alice, for example, is an internet service provider, and then it can maybe put herself in between the proxy and the website. So you rely on network topology now. Okay, That's it so far. So how does TLSNotary do it? TLSNotary uses cryptography in that it uses multi-party computation to do it. So for those of you who are not familiar with multi-party computation is, basically we have several parties, in our case 2, and you want to compute a function on some secret inputs in such a way that you don't use any other entity for that, and also that your inputs, they should remain private, right? So that's what TLSNotary does. So you have this function, and these are the inputs that stay private. And then coming to TLSNotary, that's exactly what Alice and Bob do here. They operate this MPC TLS connection. So Alice has a TLS connection open to the website, but at the same time, there's also this MPC TLS connection, right? And so the reason why TLSNotary works is that the key for TLS, so which is somehow this derived secret sharing, this G to the AB, the Diffie-Hellman stuff, that's now split between Alice and Bob, right? And in that sense, the full key is withheld from Alice, so she no longer can make up any data and encrypt it with this key. But on the other side now, Alice and Bob have to do everything for this TLS connection together, right? So they have to encrypt the requests, they have to decrypt responses, they have to stretch the keying material. All this is then done in MPC. Okay, so this was quite some sort of the general introduction to this topic. And now we want to have a look at it a little bit more in detail. So first we have our techniques which we are using, and then we go through the different phases of TLSNotary. So techniques, we have oblivious transfer, which is the core building block for everything else we do. Like garbled circuits relies on oblivious transfer, OLI, VOLI, interactive zk, everything in some sense builds on oblivious transfer. So garbled circuits you can think about as the general MPC protocol, which we use for operations on binary data, especially like encrypting requests and decrypting responses. Then we have OLI or VOLI, which is in some sense an arithmetic version of oblivious transfer, and that's used when we have to do arithmetic computations in bigger finite fields, because for that garbled circuits is quite inefficient. Yeah, and then we have this interactive zero-knowledge protocol, because we need to do some proving in the end of our protocol. Right, and here you see the phases of TLSNotary, which we go through when you do a notarization. So first we have some pre-processing phase doing computation before the connection is even open with the server. Then we have this phases which deal with the TLS key. We have the key exchange and the pseudorandom function. Then we have the traffic phase where encryption of requests and decryption of responses happens. Then the proving part with this IZK. And in the end, the commitments. Okay, let's start with cryptography stuff. So, right, so what is oblivious transfer, or what is 1 out of 2 oblivious transfer? So in oblivious transfer, you have a sender and a receiver, and the sender has 2 messages, and the receiver has a selection bit C. And depending on the selection bit of the receiver gets message 0 or 1, depending on his C input. But you have to do it in such a way now that you have only these 2 parties, and that the receiver doesn't learn the other message, only the one he selected, and the sender doesn't learn anything about the selection bit C. Yeah, and you can do that with cryptography. Right, so I should add that there are different variants of oblivious transfer. So what I just show you here is the normal or vanilla oblivious 1 out of 2 oblivious transfer. So there's random oblivious transfer where the sender cannot select the messages, or where the receiver cannot select his selection bit, and they are sort of random inputs. There's correlated OT where these messages are correlated. So that's basically M0 is equal to M1 plus delta, and the delta is the same for many iterations of this OT. So there's K out of N OT, where it's basically N messages and receiver gets K. a whole zoo of protocols. But what's important is maybe that you can get random oblivious transfer from correlated oblivious transfer, and you can get oblivious transfer from random oblivious transfer. And yeah, oblivious transfer is used a lot in our protocol. Okay, by the way, sometimes I put these paper titles here because yeah, I think it's a good starting point. If you want to look into it, then this is basically the paper which gives you a good start into this topic. Okay, so I've now talked about oblivious transfer. Now let's have a look at garbled circuits. So brief primer on garbled circuits. Garbled circuits is our general purpose MPC protocol for doing computation with not in arithmetic or bigger number fields. And the good thing about garbled circuits is that it's quite efficient considering it as an MPC protocol, because in MPC you usually have the problem that, I mean, you have some parties, you run through some circuit, and then you always have to exchange messages after some gates in the circuit. And so you always have this latency penalty in your protocol, like, because you have some network overhead, right? In garbled circuits, the nice thing is you send something in the beginning to the other party and you send something in the end, but it's not really depending on the circuit size. And especially for two-party setups, garbled circuits is quite a simple protocol. So it's ideal for our use case. So let's have a look at how it works. So we have two parties, garbler and evaluator, and they want to compute this function with secret inputs from both parties. So how does it work? So first step is we have to think about our function as some sort of circuit, right? And in a circuit, you can think about your wires. So your wires, Ci, Cj, input wires here. Ck would be an output wire, and that would be a gate, right? Let's think of an AND gate. And it helps to think of this gate as a truth table, right? So for an AND gate, you have 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. Hope that was right. And now the truth table, if you consider these values as just zeros and ones flying through your circuit, then this truth table is always the same, right? And what we do now is we introduce wire labels instead of these clear values. And think of these wire labels as basically 128-bit random numbers. So basically you translate all these clear values into these random numbers. And then these gates are now different because now they don't map zeros and ones, because now they map these wire labels to each other. And that also means that an AND gate here in the circuit is in this form now different than an AND gate there, right? Because you have these wire labels. And the last thing we need to do is now we encrypt these gates, right? So if you think about it at the truth table, you now encrypt every row of this table, and you use the input wire labels as the key, and then you encrypt the output wire label. And which output wire label you encrypt, if it's either the one belonging to the 0 clear text or the 1 clear text, that depends on the gate, right? So here in all these cases, if it's an AND gate, you would encrypt the 0 output wire label, and only in this case, you would encrypt the 1 output wire label. And you do that for the whole circuit. So one party does it for the whole circuit, garble that. And so now you send all these gates or the garbled circuit to the evaluator. And you also send the active input labels of the garbler to the evaluator. So the active input labels are basically the zeros and ones the garbler chooses for his input, but now as these 128-bit encodings, right? And now we need oblivious transfer to send the input labels of the evaluator to the evaluator, right? So because of course the garbler cannot know which input the evaluator chooses, because the input should remain private, right? So we use oblivious transfer to send these input labels to the evaluator. Yeah, and now the evaluator has everything. It has basically the first layer of the circuit, and then it can start encrypting and walk through the circuit. And then, depending on what you want to, so do you want to that the garbler knows the output, or do you want that the evaluator knows the final output? You can either send the decoding information from the garbler to the evaluator. That's basically the mapping between clear text values and wire labels, or you can do the other way around and now send the active output labels from the evaluator to the garbler, or you can do both. Okay, and there are quite a few optimizations you can do now. So we use all of these optimizations here because think of it, I mean, like you have per gate, you have like 4 rows. Each row is 128-bit. A circuit has a lot of gates, and we have many circuits, so a lot of data. So we want to make it as efficient as possible. And I don't want to go into the details here, but maybe very briefly, row reduction allows you to go from 4 rows to 3 rows per gate. Free XOR allows you to make the XOR computation locally, so you don't have to gobble XOR gates, only AND gates. So now we are at only AND gates with 3 rows, and with half gates you can cut that down to 2 rows per AND gate. And then there are some improvements to computation by using a fixed key AES for encrypting. Okay, now we have understood our garbled circuits. So we now have the tool to do MPC encryption and decryption in some sense. Because I mean, when we do encryption and decryption, the circuit which is garbled is then AES, right? I mean, depends on which cipher suit in the TLS is used, but TLSNotary currently only supports AES. Okay, but now let's come to the arithmetic part. So when we want to compute or compute over prime fields and that kind of stuff. So we have oblivious linear evaluation. What's that? So you have 2 parties, sender, well, let's not say sender and receiver, just 2 parties, A and B, and they have their inputs A and B, and they have their outputs X and Y. Sometimes X is also an input, but let's not get into the details here. What's important is that PA doesn't know anything about B and Y, and PB doesn't know anything about A and X. And what this allows you is basically to convert a product into an addition, so to say, because it returns you X and Y in such a form that it fulfills this equation, so that Y is equal to 8 times B plus X. And if you rearrange that, and we ignore the minus for here because you can rewrite it as Y plus minus X, then you have your inputs which are basically a secret shared product, and you arrive with a secret shared sum. So that's why this is also called M2A when we talk about that, because it converts from multiplication to addition. So why is this called oblivious linear evaluation? One might wonder. That's because now PB evaluates Y of B. So it basically evaluates Y, or the linear function Y at the point B. Right? And it evaluates it obliviously because PB doesn't learn the function Y, which is defined by A and X, and also PA doesn't learn the point where this function is evaluated, which is B. And it's also, this construction is also the building block for the so-called reverse protocol, which allows you to go from an addition to a multiplication, and it's also heavily used for interactive zero-knowledge proofs, or at least in our IZK protocol. So maybe what I can add is that there's a vector version of it that's called volley, and that's just that now the receiver evaluates many different functions at the point B.
Which is much more efficient than evaluating them individually.
Correct, right. Okay, so that's it so far for.
We don't want to take questions.
No question, only in the end. Okay, so now we have looked into, so to say, the core building blocks for cryptography. Now let's look at it's the TLSNotary protocol. So the first thing in TLSNotary is the pre-processing phase. So what does it mean? Like, think of MPC, we need to do a lot of computation, and when there are you have an open TLS connection to the server, there might now be the problem that you run into timing issues because you keep the connection open for too long, right? And then the server will just quit the connection, and that's not nice. So we try to do everything we can upfront before opening the connection, and this is the pre-processing part. So the first thing you need to do is you specify the expected traffic before, right? So we have these values, max send, max receive, and max receive online. I think max send and max receive is pretty clear, and I'll tell you, I think in 1 or 2 slides what max receive online is, but think of it as specifying the expected traffic, because depending on the traffic, you now know how many AES circuits you need to garble, right? So specify that upfront. And once we've specified this upfront, then we run our oblivious transfer machinery in some sense. So I showed you oblivious transfer, so you can do oblivious transfer with this CO15 protocol. That's what we use. That's a very simple oblivious transfer protocol using public key cryptography. The thing is now that is not very performant, doing public key cryptography for a lot of operations. So there are oblivious transfer extensions, and what they do is they sort of use symmetric key cryptography to basically boost the numbers of OT, or to artificially blow them up, so that you don't have to do all the OTs with public key cryptography. And we have 2 oblivious transfer extensions. One is COS15, which is a maliciously secure version of the IKNP protocol, which in some sense is, you use I think random oracle assumptions and symmetric key cryptography to blow up the amount of OTs you have. And we use these extensions for most of our protocol, so especially garbled circuits, encryption, decryption, and also for the key phase where we use garbled circuits. Right, but when we do interactive zero knowledge, or our interactive zero knowledge protocol is extremely OT hungry, so we have to come up with an even far more efficient oblivious transfer extension, and that is Ferret. Ferret is a protocol which relies on an additional cryptographic assumption, which is LPN, and it has quite some setup costs, but after that, so once you've set it up, it really can produce very, very huge amount of OTs very efficiently. So that's where we use Ferret. And you can think of it bootstrapping it like, first you create your base OTs, then you use these base OTs for the COS extension, and then you use COS for Ferret.
What's the Ferret assumption?
Learning parity with noise, LPN. Yeah. I mean, that's basically, I think when you have a matrix and some secret input, and you with secret input vector, and when you multiply that and you add some error, then you get some output, and without knowing the error and the secret, you cannot really differentiate, I think, the output from just a random vector. Hope that was correct. Okay. So now we have done our OT setup, and now the prover, because he knows the traffic which is now expected, we can garble all the circuits before opening the connection. Right? So especially this is encryption and decryption circuits, and also in key exchange and for PRF we have garbled circuits. And you can also set up the interactive zero knowledge protocol, as it's mostly like, I think, correlated oblivious transfer in the beginning. Yeah. Okay, so now we have done our pre-processing. Now we open the connection, and now we are in the key exchange. You probably have seen similar things before. I mean, you can think of it as in normal TLS, you have the key exchange. It's just no Diffie-Hellman key exchange, right? Public key one way, public key the other way, then G to the AB, and you have your shared secret. And this is in some sense two-party, or three-party, depending on how you consider this version of it. So how does it work? So verifier has a public key, sends it to the prover. Prover adds his public key on top, and then sends that both to the server. I mean, for the server, it's just some public key point, right? Some elliptic curve point, right? And then the server sends his public key to the prover, and prover forwards also that. And now the prover and the verifier can locally combine their private key with the server's public key. And then they already arrive at a secret shared version of this shared secret. So you have this G to the AB, but it's now basically split between these two parties. But the way it's split under an elliptic curve point addition. And this is not ideal because elliptic curve point addition is not so nice when we do garbled circuits, and it is an input to garbled circuits. So what we here have to do is we convert that from an elliptic curve point addition sharing into just an ordinary additive sharing. Right. And here you see that why TLSNotary works, right? So the prover doesn't have the full shared secret here. So he can't make up any traffic and pretend it comes from the server. Okay, so now basically we have we ended here, and we basically have a secret sharing of the PMS, the pre-master secrets, that's this G to the AB. And now we need to stretch it to get the session keys. So you can roughly think about it that this PMS is now your input into a very sophisticated construction of SHA hashes. That's how what the best way to think about it. And here I've brought you what is the pseudo-random function for TLS 1.2 AES GCM. So that's the cipher suite, basically. And we have this p-hash function, which is a concatenation of two pi functions. And this pi is just an HMAC with SHA-256. So HMAC is a keyed hash function. So you hash something, but somehow a key is involved there. So when you want to check this hash, you also need to know the key, which is usually kept secret. Anyways, we use it here to stretch the PMS into the MS and then arrive at the session keys. So I will explain in a second what this AI is, but you can think of it, it works like you have the PMS, you put it here into this p-hash value, and what you get out is the MS, and then which is the master secret, and then you have to do it again and put the master secret into this as the key, and then what you will get out are the session keys, right? So these AI are again HMAC calls with SHA-256, which are recursively defined. So this A0 is just some sort of fixed string. It's in the first iteration, it's master secret. In the second iteration, it's key expansion. And you have some seed, which is some sort of per session randomness in TLS, right? So this, I think, 32 byte of randomness from the client, and this is 32 byte of randomness from the server. And you can think about this HMAC call just as a clever way to invoke hash function and working around attacks like, I think, length extension attack is prevented by this HMAC construction. So what you do is, this H is just SHA-256 call, and you have your key, you XOR it with a constant, concatenate the message, hash it, and then again concatenate the output of that with the key, which you before XOR with another constant, and then hash that. So this is the HMAC call here. And all of this is, like I said in the beginning, think about it as like SHA-256 a lot of times in some sophisticated way. So what we do is we do this in garbled circuits, right? I said input is PMS shares, and now you do this to arrive at the session keys. And the session keys, these are the symmetric keys, which are then used in the online phase for encrypting requests and decrypting responses. Okay, so now we are in the traffic phase. That's encryption and decryption using this AES GCM cipher suite. So AES GCM is just AES in CTR mode attached with some sort of MAC or some tagging mechanism, which is ghash. So that's why I put AES CTR here, because here we look at just an encryption part, and in the next slides we'll have a look at ghash, and this both together is then AES GCM. Okay, let's first look at the request encryption. I think the only important thing here is, so you have the prover with the CWK, that's the client write key, that's part of the session keys. And now both use their CWK shares, and now the prover inputs the plaintext. Then they run this AES-CTR in garbled circuits, and then the output is a ciphertext, and you output the ciphertext to both prover and verifier. Yeah, and then the prover can send over the request to the server. So response decryption is similar, but a little bit different. Also prover and verifier. Now instead of client write key, you have the server write key, and input is the ciphertext. The ciphertext is a public input. That's why both parties input it here. You run AES-CTR again on this. And then what you get is the plaintext, but this time you only return the plaintext to the prover, not the verifier, because yeah, you don't want to leak any information about the traffic.
How is this ensured?
What?
It seems like the verifier could get the plaintext too, right?
No, because I mean, what you see here is garbled circuits, and depending on if you send the decoding information or if you do it the other way around, this basically determines who gets to see the output. So we have here, coming back to a few slides before, where we had this max received online, max send, max received online. So here's an optimization you can do, which we call defer decryption, and it's enabled by default in TLSNotary. So that means when you just have a request and a response, so no more cycles, request, response, so just request, response single time, what you can do is you can defer the decryption until after the online phase, because as soon as the connection to the server is closed, there is no need anymore to keep the keys secret from the prover. So you can decode basically the keys, and the verifier can send over his key share to the prover, and now the prover can just decrypt locally, right? So you don't incur any MPC or 2PC overhead here for decrypting the response. And this is this max receive online value. So usually it's just 0, but you may need this if you have, like, if, for example, think of a case where your request depends on the response before, then you might want to do this. But usually, I think 90% of the use case is pretty fine to defer the decryption. Okay, now we've talked about AES-CTR, but what we use is AES-GCM, so we have to look at ghash. So what is ghash? Ghash is basically a MAC on these encrypted messages to make or to ensure the authenticity of the message. And you can think about it as basically two parts. So you have this J0, and then what you add on top of J0 is basically this sum term, right? First, think of all these values, J0, H, and B. They are element of an extension field, 2 to the 128. And now what are the things here? So J0 is just basically AES-CTR using the key, some nonce, and an IV, and the counter set to 1, and then using this on all zeros. So what it's just the key stream. And H is AES in ECB mode, where you just use the key as the key, it's a session key as the key, and then encrypt all zeros.
Could you remind us about the modes? Like, at least I don't remember CTR versus ECB.
Yeah, okay. Yeah, ECB is just, so AES is 16. So AES is 16 bytes of key and 16 bytes of message, and run that through the AES circuit. Boom, arrive at ciphertext. AES-CTR is you have 16 bytes key, and then what you encrypt, the other 16 bytes, is now in TLS. You have I think 4 bytes IV, which is determined by it's in part of the session keys. Then you have like 8 bytes of explicit nonce. That's implementation dependent, but usually you increase some sort of counter. And then you have 4 bytes of just counter per TLS record. And this is, so what you encrypt, so you have 16 bytes of key, and what you now encrypt is concatenated 4 bytes IV, 8 bytes explicit nonce, 4 bytes counter. Encrypt that, and this output is the key stream you now use and XOR it with 0. And XORing with 0, I just use this notation that I can write AES-CTR, but it's just the key stream out of this, right? And what's important is that this J0 works as a mask on this term, right? Because if you wouldn't have J0 here, I think you could invert that and basically arrive at your H.
And ECB was the naive.
That's a naive one, yeah. That's the mode you should never use, because it this is with the picture with this penguin where you use AES and ECB mode. Yeah. Okay, and this B is then the message bytes now interpreted as part of this extension field. Right, and yeah, basically then you have the job of computing this part, and you can compute this part AES CTR. You can just do it in garbled circuits, right? Because it's just an AES call. So you compute two shares of J0. And for the other part, which is this sum term, this is a little bit more involved, because first you have to compute this H. So you can also use garbled circuits for this AES ECB call and then return a sharing of H to each party. But now you have this power here, right? So you have to raise H to some higher powers. And the maximum value, I think, is 1026. So you have to do quite a lot of operation in an extension field, and that cries for our A2M and M2A conversion protocols. Yeah. Okay, so now basically we're done with the traffic phase, and now we have to prove stuff. So why do we have to prove stuff? I mean, we have to check that the prover behaved honestly, because like think of prover not garbling an AES circuit, but just a circuit which leaks the verifier key, right? So this would be a problem. So we have to make sure that this doesn't happen. And the nice thing is now that we can use a zero-knowledge protocol to ensure that. And the reason is now that after the TLS connection, the verifier has no secrets anymore, right? Because he doesn't need to protect these keys any longer because the connection is closed. So you can decode these keys and then use a zero-knowledge protocol with the keys as a public, the verifier key shares now as a public input. And we use, an interactive zero-knowledge protocol is ideal for our setting. We use Quicksilver. And I won't go into the details of how Quicksilver works, but maybe very shortly, it's in some sense for all the prover inputs to all these circuits, you create max by using subfield volley. The subfield volley is just some sort of fancy term for correlated oblivious transfer, I think for a binary field, and then I think it's then the same. And what you do is, now you have these, if you look at this equation here, so you think about as this UI is basically the 0 or the 1 from the prover input used for a circuit, right? And then you have a delta, which just the verifier knows, and then you can use this correlated OT to create these MI and KI values. So MI is 128-bit of random MAC for every 0 and 1 input of the prover to the circuit, and then you have the same for the verifier, and they fulfill this equation. And now you work through the circuit, and in the end, or you work through all of the circuits, and in the end you can then check if this equation still holds. There are some tricks you need to do for multiplication gates, but not going into the details, but it's quite efficient protocol, and we use that. So yeah, like I said, you decode the verifier secrets, and then they are public input for our zero-knowledge protocol. And what we do now is basically we prove all garbled circuits computation, and also the prover has to prove that he knows the clear text of the server response. I mean, if you think back to this decryption, when I showed you this picture of the decryption, the plain text was only returned to the prover, right? So that's the reason why a prover now has basically to prove that he really knows the clear text, and that it encrypts back to the ciphertext which was observed by the verifier. Yeah, maybe interesting to mention here is this optimization, which is called the decode server write key for verifier. So we haven't implemented it yet, but the idea is so if the server response has no secrets, like if there isn't anything inside the server response the prover wants to hide, so basically if it's public, what you can do is you can use the server write key and basically return or decode it for the verifier. So and then the verifier can basically just can just encrypt or decrypt the server response on its own, and then you don't have to do this second step. And this optimization, together with the deferred decryption, allows you then basically to notarize. You don't incur any overhead for notarizing megabytes or gigabytes of data anymore.
Why interactive, ZK?
I mean, we anyways have to, because of the TLS notary setup, you anyways have to, I mean, you wouldn't really have any advantage from using snarks in this situation. So in considering performance numbers, this is the ideal use case. Okay, so yeah, now we are nearly done. We only need to create commitments. So yeah, how does this work? So first we have these keys here, right? These are the keys from the verifier, and these are the max from the prover. And now you adapt these keys so that you can derive them from a single PRG or from a single seeded PRG, and then you can send the delta of the now new PRG, the new keys added, and you add this original key. And you send it over now to the prover, and this allows the prover also to adapt his max. So the idea is just that you can derive all of these labels just from the PRG with a single seed. And now the prover can create commitments for the traffic, right? He creates blinded commitments and includes them in a Merkle root, Merkle tree, and then he sends the Merkle root to the notary. And now the notary creates a signed attestation. So there are many things in this attestation, but for now let's just concentrate. So what's in this attestation? You have this secret from the PRG. You have this delta. The delta is basically this, and that's what you need to go from the 0 encodings to the 1 encodings. Right, and it includes the Merkle root. And then the notary sends this signed attestation to the prover. Yeah, and now the prover has the signed attestation, and now he's able to create presentations for verifiers. Yeah, so I mean, the commitment form we are using here, right? This is basically these garbling labels, or these this 128-bit wire values. But at some point we want to support other commitments, like probably SHA-256, and we also talked about maybe supporting AES commitments, so like the ciphertext itself. Yeah. Well, but probably SHA-256 probably most important for the next time. Yeah, I mean, that's it. Thanks so far. I mean, I've put here some links, like this is our website, then we have a proof explorer where you can check basically what's inside a TLS notary proof. We have some documentation we need to improve. This is our library, and we have some JavaScript bindings and also working on a browser extension. Yeah, thanks.
Do you have any
Questions now or over pizza? Do you have pizza yet?
Yeah. Or
Do you want to take some questions now, or do you prefer?
Yeah, sure.
Any questions? For Thomas? There's so much information. I had a few questions. Yeah. So, what's the rationale behind GCM? How is that better than CTI again?
I mean, so
And is that the go-to, like AES?
yeah. So basically in TLS you can basically the client and server can negotiate the cipher suite which is used, and we see that once there were many ciphers supported, but they're all being deprecated, and AES, so to say, is AES GCM is the standard. I think even in TLS 1.3. So currently we only support TLS 1.2, but even in 1.3, I think it's the gold standard AES GCM. is just this ASCTR in counter mode, and then you use this G hash for the backup. So
What's the advantage over CTR?
Basically that on every message you attach a tag, and you can now verify the tag if the message was corrupted in transit. So,
Also, the computation is for only one small setting. It's not very close.
yeah, that's but also true for ASCTR, right? So
I'm talking about, yeah. It's the one to use for
Are you asked?
That's what mark is. It's the authenticity of it.
I thought that like non-manipulation would be provided by at least non-malicious by TCP already. But that would would assume like retransmissions and stuff like that. Are we talking about malicious manipulation?
No, like there's some evil entity in between which flips back the message bits.
So what are the overheads? So I was sort of, what are the overheads?
For TLSNotary versus TLS?
Yeah.
Oh, big. I mean, that's always the problem. Like,
But again, I understand there must be a trade-off. We are doing private ones, but what's the ballpark?
what's the ballpark? I mean, like in running time or?
Yeah.
I think bandwidth is the only thing you really think about, right?
Yeah, I would say it's between 10 and 100x.
Okay. So then
Could you say you also?
Well, I think to be precise, you will need to split it into three parts. There is a constant part, there is an overhead on the request, or maybe sent from server and received from and the other way around.
I mean,
There are three different overheads.
There are parts you always have to do. For example, all this key exchange, then the whole PRF. PRF is a huge circuit, like you have some offset, and then from there on it depends on which mode of operation you use, and also like how big is the traffic, like the request or the response. Yeah, but it's big overhead.
The exchange itself is how much bandwidth?
Sorry?
The key exchange itself is how much bandwidth, do you remember?
I don't know. Yeah, 56 megabytes, I think.
Just the key exchange.
But that's more than 100x.
Yeah, I mean, I would say,
That's a
it was like,
It's constant.
you have a small request and a small response size, then I think.
All from one.
All from, yeah.
And then there's 10,000 on the request, I think.
So it's 50 megabytes.
Just for the key exchange. In
In
bandwidth.
of upload. That's
Of
also
upload.
Because you know the experiments with the cryptographic agility that they did, Google did with the TLS, etc. So when you try to make a TLS post-quantum, and basically you change, you don't use ES anymore, but you use 10, and so the key sizes are much bigger,
Yeah.
but they are not so much bigger, so you go to 2-3 megabytes, kilobytes. So and it goes, then the cascade goes too slow.
So, and you know who's the winner of that? The internet providers.
Yeah.
And cloud computing.
Yes. But I mean, at the same time, you get Linux next to I mean, 10 to 100 for obliviousness, as we are now with the business protocols, is kind of normal. It's not true. It's not true.
Do you have an intuition for gobbling? Like it feels like there's two different gobbling steps. Like I struggle to like
Yeah, I can see
actually
that, but
understand.
basically, this was the intuition. I mean, it's like,
So specifically, there's some randomness in the wire labels W, I, and J, and then we also have encryption.
yeah, so
What is this?
yeah, think of it like this part is set here to hide the clear text values, 0 and 1, only the garbler knows it, right? But now the thing is, if you wouldn't encrypt the circuit, the evaluator could basically move from the true path. He could at some point basically flip a 0 to a 1 and then evaluate the circuit differently than it would have been dictated by the input sequence.
Yeah.
So you have to basically encrypt it to ensure the path through the circuit.
And how is the randomness for the wire labels? created to
Right now, that depends on, so usually you can just use some simple PRG, but then at some point, when you use this optimization, especially this, what's it called? I think it's free XOR, then you use the global delta. So for every, if you use free XOR, then for every while label, you have, for the 0 while label, you have this random number. And if you want to get to the 1 while label, you add delta. And the delta is global per circuit. This allows you to make these gates, basically the XOR gates, for free.
And this is a constant mapping somewhere, right? So, how do I get from plain text 0, 1, 1, 0 for the input wire into the randomized version of it?
Yeah, I mean, you have a PRG. You have this PRG has a seed.
So I seed it with the actual like plain text. Or what?
No, with some,
I run
and then you use some running number k, and then for each gate you order that into some.
and it's a constant mapping table somewhere.
I mean, what do you mean by constant? You have to do that. You can only no. You only evaluate the circuit once. No evaluating twice with different inputs. You have to double again.
Nice.
Yeah.
Any intuition for how encrypting a gate even works?
Yeah. So think like this is the truth table. So think of a row. Like here we have 128-bit strings, and you use these wire labels, and then now so for example, you encrypt the output wire label. Let's assume it's an AND gate. Now what you do is you encrypt the output wire label, and use these as a key, right?
I think when I focus really hard, I can understand any part of the protocol except the currency.
Yeah, same.
Yeah, I think it probably.
It's just there's a lot of moving parts. There is wire, there is encryption, encoding. But we're gonna make the TK money, so and it's very.
But envisioning the encryption, when thinking about truth tables, that helps me. Like that makes sense. Like you can't think about hardware anymore. You don't encrypt hardware. Okay, so this is my.
I think it's a good intuition, but it's only part of it.
So I think you have a typo, I think it's slide 2. I think you have a typo at the slide 2.
Why is it?
You were the point in which you were showing the diagram of your
I think slide number 2.
PR and PS, but then the text you go to
Which slide number 2?
Number 2, I think.
What that was?
Almost at the beginning.
Was this?
That's not how it's called too.
Where's the title?
Next.
Almost two.
Next. Here. It should be P and P, right?
Oh yeah. I mean, yeah. Sender and receiver.
Because then
Now I see. Okay.
because you have PA level.
Yeah.
Not bad. And at some point you said you're switching addition of elliptic points to some kind of normal addition.
How?
Yeah. And now we come to the backup
That was
part.
my question.
We can go through that.
Yeah, let's do it again.
Okay.
The whole presentation.
Okay, so this is the OT protocol, base OT. This is our OV or VOLV, how you can do it. But you are interested in this key exchange. Do we want to do this, or do we want to do this after what's in the file?
We can grab some pizza and eat while
Okay.
talking.
Yeah, let's do that.
Yeah.
Thomas, thank you so much.